Vocabulary. Here it comes.
For organic.
20 words.
Ready for your quiz.
Bust them out.
Here we go.
Homologous series or homologous series of hydrocarbons. Reference table Q. Hit us with a definition, Melks. Group of hydrocarbons, similar chemical formulas. They're very similar, so they can be very tricky, but if you pay attention to table Q, you will see that they are only different in their number of hydrogen atoms and the number of double, single, or triple bonds. So go to table Q.
Facts. Table P, organic prefixes. The number of carbons in the right column will give us a prefix in the left column. That's one of the major tools we're going to have for the whole unit. Mm-hmm. The words that tell us how many carbons from the backbone are in the molecule, we will use table P repeatedly for that.
Functional group, another big reference table that looks very, very scary because of the different classes, the functional groups, the general formula, the examples, and a lot of stuff going on here.
Great reference.
Hit me with a definition, notes.
Gotcha.
It's the part of the molecule that makes it different from plain old hydrocarbon, with carbon and hydrogen. When you introduce nitrogen, oxygen, a halogen, it changes the molecule and changes the pattern in the bonding. It changes the pattern in the naming. And we call it a functional group because it makes a molecule behave a different way.
There you go.
Table R.
Function. Alkanes. This is the basic first thing we'll study. Mm-hmm. Alkanes, you'll see here's 3 examples. This is all single bonded carbons. Right, so any hydrocarbon, hydrogen and carbon, that's it, hydrocarbon, that contains all single bonds between the carbons. That is an alkane.
Yep. Alkene. Well, we've got some examples. Ethene, propene, butene. You notice the pattern in the end of their name. It has ENE. Hit me with the definition. Got to have a double bond between some carbons in that chain somewhere.
At least one.
At least one. Sometimes 2 or 3, but we're only really going to deal with 1.
Yeah.
Alkenes, double bond.
Right. Alkynes, notice this picture now. We got ethyne, propyne, some of those similar prefixes, but the ine changes, and notice there is triple bonds.
I saw some numbers in there too.
Oh, good. And we're going to teach you what those numbers mean too.
They're addresses.
Yes, they are. Really. I never actually heard you say that.
It's an address.
It is. I like that. Mm-hmm. That's cool. Hydrocarbons that contain at least one triple bond in their carbons is an alkyne.
So recap, alkanes, single bonds, alkenes, double bonds, alkynes, triple bonds.
And the table's there, so if you forget, you use the table to figure it out. Mm-hmm. Okay.
A structural formula. I hope these are looking familiar because we've been doing them for a while here. We've done them through other units. We're spiraling back. It's a simple diagram that shows us the number and arrangement of atoms. It has a lot of information because it tells you all of the atoms, each type, and exactly how they're connected in their little local neighborhood network.
Yeah, that arrangement of atoms is key because that's the bonding.
Yes.
Single bonds, double bonds,
triple bonds, carbonyl.
Now, unfortunately, the molecular formula doesn't show us that. Mm-mm. You see there, glucose, butane, octane, those are words we'll use, butane and octane.
For sure.
Just tells me simply the number of carbons and hydrogens. So it's a symbol that shows me how many of each element. Doesn't really tell me a lot about their arrangement or their bonding. I would have to dig deeper in order to figure that stuff out.
Doesn't show us how they're connected. Isomers. Well, here's 3 isomers, 1, 2, and 3. If you're careful and you count, you'll find out there's the same number of hydrogens and oxygens and carbons in all 3 of these. It's when 2 or more molecules have the same number of each type of atom, but the way they're connected makes a different arrangement. So their local networks are not exactly identical, even though their molecular formula might appear to be.
Right, so they're going to have different functions, different names.
Yeah. Straight
chain hydrocarbons. So hydrocarbon, hydrogen and carbon, straight chain. Just like it says, so those carbons are a straight chain all the way across. So it's a simple, this is where we'll start. We'll start with simple hydrocarbon chain that has no side chains or functional groups, which is those funky other atoms that could be in there.
Then we're going to start building things off of them, like branches and double bonds. And here's an example of some hydrocarbons that have branches. Notice things like numbers for addresses start showing up, and anyways, they get more complex, right?
Yes.
So a branched hydrocarbon is kind of like a tree that's got branches. It's off the main chain. It's got things hanging off of it. It's got 1 or more carbons attached to the side of the chain. It's not just a straight chain anymore. It might have a dangly or 2 danglies or whatever it may be.
Yep. We'll learn how to name those pretty easy.
Yeah.
Saturated. Now there is saturated hydrocarbon. Hydrocarbon, again, tells me just hydrogen and carbon. Mm-hmm. We did saturated before with solutions. That means it's all filled up.
Right.
So what that means is these carbons are holding the maximum amount of hydrogens that it can.
Mhm.
And these just so happen to be what we call the alkanes. When they're single bonded
Right.
carbons,
Yep.
now they're holding as many hydrogens as they can.
Only alkanes are saturated.
True that.
Alkenes and alkynes are unsaturated hydrocarbons because there's a double or a triple bond in there, meaning that carbon is not holding as many hydrogens atoms as it can because there's a double bond in there tying up spots. It's connecting carbon twice or three times that
Yeah.
hydrogen can't take that spot anymore.
Right. It's almost like somebody double, parking us in two spots in the
Yeah.
parking lot.
So alkenes and alkynes are unsaturated.
Sure. Polymerization reactions. So these little yellow guys are what we would call monomers.
Yep.
And if I link them together, I make a polymer.
Right.
So linking a bunch of monomers together makes that. So a reaction, this is one of the 7.
Yeah.
Right, that links many monomers together in a large chain. And I remember at Kodak, we used to be really good at controlling these reactions with temperature and time. And we let it go for a certain amount
You
of
mean
time.
collision theory?
I'm saying.
Yeah. Fermentation, any reaction that
Yum.
will produce alcohol as a byproduct. These typically use an enzyme or a biological molecule that is carbon-based, but way more complex than what we would study here in terms of its structure. It takes sugar, eats it up, makes alcohol.
Yes, and we will find that alcohol is one of those functional groups.
Mm-hmm.
Table R. Combustion, I think we all know what that means.
Fire.
Fire. So, a reaction specifically that burns a hydrocarbon
Mm-hmm.
in the presence of oxygen,
Oh,
therefore
yes.
it is a reactant,
Two reactants, hydrocarbon, oxygen.
forming carbon dioxide and water, both products,
Yep.
will always be present.
Exactly.
These are fun ones to balance. I like these ones.
They're difficult. That's why he likes them.
It is. I like math.
Saponification.
What we
if you
making?
break the word down, saponification sounds like soap to me.
Well,
And I love this. I got stories. I'm going to even try and make some this year again. I've done it in the past. It doesn't always come out usable, but I'm going to try.
I have a friend family where the whole family does actually have
Making
their own
soap.
Yeah, and they have
The thing with making soap is that it requires really some serious base, like
lye.
strong base.
Lye usually.
And so after you make the soap, you actually got to let it sit around for like weeks or months to calm down
Cure.
before you really use it.
And
Otherwise,
it's
you get
cure.
all itchy and you
Yep.
get chemical burns.
So
Sorry.
esterification is another reaction, and this is going to make what we call an ester. And you'll find an ester is also a functional group. You can see a picture of it.
Mhm.
And I need to take any organic acid
Yep.
with any alcohol, now that we have alcohols.
Yep.
And I can make an ester in water, and you'll see that's a dehydration.
Synthesis.
Yep, dehydration synthesis.
Esters are
So
cool.
this is a reaction where an organic acid reacts with an alcohol to make an ester. And
Esters
if you
typically
take
are
college and
smell.
chemistry, they have a lot of stuff. You take organic chemistry,
And
college,
in
there's some smelly
1920
stuff.
or 1930, they figured out how to make a polyester, one of the first polymerizations,
of
and
esters.
gave us nylon and stuff like that, which is in all our clothes now. But anyways, a substitution reaction sounds exactly like it says. You're going to substitute something for something else. So in this case, we're substituting a chlorine for a hydrogen.
Right. Slow swappy route.
So a reaction where an atom of one molecule switches with an atom of another molecule. This is literally like a single replacement, but with organic molecules.
Specifically.
Not ionic ones, which is how we studied single replacement and double
Right.
replacement.
Right. And then, so now addition is I'm just going to add those chlorines onto the other molecule. No substitution happens. Let me break those chlorines up and stick them on. Notice there's got to be a double bond now in the hydrocarbon. So this is a reaction where an atom of one molecule is simply added to another
another.
molecule,
Yeah.
making a bigger molecule.
Yeah, we got any more? Whoa, that's it. That's all, folks. Thanks for watching. Do your
Don't forget
quiz.
your quiz.
I pressed a button and it stops.